Do you remember the exact moment the heavy iron rules of the open pit changed forever? It was Chino Mine, New Mexico, 1963. On a punishing 8% ramp climbing out of the Santa Rita pit, a 65-ton mechanical drive haul truck attempts a desperate downshift under a crushing load. The torque converter stalls, the driveline shudders violently, and the transmission drops a gear, bringing the entire production cycle to a grinding halt in a thick cloud of dust and diesel smoke. Moments later, a different silhouette approaches that exact same steep grade. It is hauling an 85-ton payload. It does not downshift. The engine pitch remains a constant, screaming high idle, yet the massive truck pulls smoothly past the broken mechanical hauler. This was the unit-rig Lectra Hall M-85. Beneath its heavy steel deck plate, there was no transmission, no driveshaft, and no torque converter. The rumbling diesel engine was merely a prime mover, turning a massive generator that sent raw electrical current through thick cables directly to General Electric traction motors housed inside the rear wheel hubs. By stripping out the heaviest, most failure-prone mechanical components of a traditional drivetrain, engineers managed to increase the payload capacity by 20 tons. But this sudden, brutal transition from mechanical torque to high-voltage direct current created an immediate crisis in the maintenance bays. The men who opened the electrical control cabinets of this new machine were staring at 600 volts of lethal current, and it terrified them. Breaking the 65-ton barrier was a monumental leap for mine production engineers. But moving 85 tons of iron and copper ore uphill was only half the physics problem. The true danger in any deep open pit operation is bringing the massive kinetic energy of that vehicle safely back down the ramp. Traditional drum or shoe brakes glazed over, boiled their fluid, and failed catastrophically when forced to hold that much weight on an 8% downgrade. The M-85 solved this by utilizing the General Electric system to introduce dynamic retarding to the open pit. By altering the electrical circuit, the traction motors in the rear hubs were turned into massive generators. The physical resistance of generating that electricity acted as an invisible brake, slowing the truck without a single piece of mechanical friction. This process converted the truck's kinetic energy into immense amounts of electrical heat, which was then dumped straight into the atmosphere through a bank of metal resistor grids mounted just behind the cab. Transitioning to this electric behemoth required operators to unlearn decades of hard-earned physical muscle memory. For a veteran accustomed to double-clutching a mechanical transmission and driving by the deep sound of the engine revolutions, the cab of the M-85 was disturbingly quiet. The heavy gear shift lever was gone, replaced by a simple forward and reverse directional selector. The throttle did not mechanically govern the wheels. It was a sensitive rheostat, commanding the generator to send more electrical current to the rear hubs. This disconnect between the diesel engine and the drive wheels created a hidden, unforgiving danger. If a standard mechanical truck was bogged down under an 85-ton load, stomping the throttle would simply stall the engine or snap a drive shaft. But if a green operator stomped the throttle of an M-85 from a dead stop, the sudden demand for massive torque sent a violent surge of high-voltage current straight to the traction motors. Before the heavy armature could even begin turning, the electricity would arc across the commutator bars, creating a brilliant, destructive plasma flash. The mechanics called it a flashover. It instantly vaporized the copper components and left the truck completely dead on the ramp. To prevent it, the veteran operator had to ignore the screaming sound of the diesel engine, which revved to maximum instantly to power the generator, and instead stare intently at the ammeter on the dashboard. They learned to feather the pedal, feeding the current slowly, letting the electric torque build to overcome the immense inertia. It was an entirely new philosophy of machine control. But that philosophy was violently tested when the monsoons hit New Mexico and the 8% ramps turned into slick, unpredictable grease. A mechanical haul truck relies on a differential to lock the rear wheels or distribute power when traction is lost. The unit rig M-85 possessed absolutely no mechanical link between its two rear wheels. The General Electric traction motors operated entirely independently. If the left rear tire hit a patch of slick mud while the right tire maintained its grip on the bedrock, the left electric motor would instantly lose physical resistance. The sudden lack of load caused the electric wheel to overspeed violently, sending a massive voltage spike back through the control cabinet. Simultaneously, the right wheel, still gripping the rock and receiving full torque, would drive the truck violently off-center, slewing the 85-ton mass sideways toward the safety berm. Operators had to catch the wheel slip in a fraction of a second, dumping the throttle before the electrical surge could trip the ground relays or tear the planetary gears apart. The General Electric motorized wheel was an undeniable engineering masterpiece, but it housed highly sensitive electrical components and complex planetary gear reductions inside the exact same steel rim that was constantly submerged in acidic water, abrasive copper dust, and brutal vibration. If the rubber lip seals on the hub failed, the mud infiltrated the commutator. A single breach meant the truck had to be towed to the shop, where mechanics would painstakingly extract the heavy, contaminated motor assembly from the axle housing. It was a highly specialized, agonizingly expensive repair that frustrated old-school mine managers to no end. Yet, despite the fragility of the electric wheels in the mud, mine planners immediately began redesigning the entire geometry of their pits to accommodate them. The economic impact of the unit rig M-85 was not measured in payload alone. It was measured in the shape of the Earth. Mechanical drive trucks required a shallow grade, usually around 6%. Every time a driver depressed the clutch to shift gears on a grade, the heavy truck lost precious forward momentum. If the ramp was cut too steep, the truck stalled before the next gear could fully engage. The electric drive system eliminated shifting entirely. The General Electric traction motors applied continuous, uninterrupted torque from zero to top speed. Mine engineers at Chino and Bingham Canyon realized they no longer had to limit their ramps to 6%. Because the M-85 did not lose momentum-shifting gears, they could cut the haul roads at 8, or even 10%. Steeper ramps meant the overall diameter of the open pit could be tighter. A tighter pit diameter meant stripping millions of tons less of unprofitable waste rock just to maintain the required high wall angle. The electrical power of the machine physically altered the shape of the mine, making deeper ore bodies economically viable. But as the trucks grew from 65 tons to 85 tons, and the haul cycles sped up on these steeper ramps, the mechanical rhythm of the loading face was shattered. In the early 1960s, the standard electric mining shovel in a copper pit possessed a dipper capacity of around 6 cubic yards. Loading a 65-ton mechanical truck required about 7 or 8 passes. It was a perfectly acceptable cycle. When the massive M-85 arrived, filling its bed with a 6-yard dipper required 10 to 12 passes. The loading time stretched. Trucks began queuing at the shovel face, idling their diesel engines and burning expensive fuel while waiting for the undersized shovels to finish the job. The bottleneck had simply moved from the ramp to the bench. The M-85 proved that haulage capacity had violently outpaced loading capacity. This forced manufacturers like Harnisch-Fager and Bucyrus-Erie to radically scale up their own designs, rushing 10 and 15 cubic yard electric shovels into production just to keep pace with the new electric haulers. The entire industrial supply chain had to expand. As the physical size of the machinery scaled up, the maintenance demands shifted entirely from heavy wrenches to high-voltage diagnostics. The typical heavy equipment mechanic of the early 1960s understood torque converters, planetary gears, and hydraulic pressures. They diagnosed problems with a wrench, a rag, and their hearing. The M-85 introduced a large steel box mounted on the deck, directly next to the cab. This was the electrical control cabinet. Inside, heavy contactors snapped open and closed, directing over 600 volts of direct current from the generator to the wheels. This was a lethal voltage limit. A dropped wrench across the wrong terminals would not just cause a spark, it would create a catastrophic arc flash capable of vaporizing steel and killing the mechanic instantly. The maintenance culture had to undergo a brutal, immediate evolution. Diagnostics shifted from mechanical teardowns to multimeter readings and Megger testing to check winding insulation. The mechanics had to learn to respect invisible, deadly energy. Dust and moisture, the two absolute constants of any open pit, were now mortal enemies of the drive system, capable of causing devastating electrical shorts within the cabinet. The transition was dangerous, and it weeded out mechanics who refused to adapt. Yet, despite the lethal voltage and the fragile electrical seals, the operators out on the bench were discovering that the electric drive system possessed a very specific, undocumented physical rhythm when pushed to the absolute limit. The maintenance manuals provided by Unit Rig and General Electric in the early 1960s were filled with complex electrical schematics, but they lacked the sensory data required to keep the M-85 alive on the bench. When the fierce American Southwest summer pushed ambient temperatures past 100 degrees, the cooling blowers struggled to dissipate the heat generated by the 85-ton climbs. The copper winding insulation inside the wheel hubs would begin to bake. There was no digital alarm for this. The veteran operator learned to detect thermal overload right through the soles of their boots. Before the insulation completely failed and grounded out, the electrical resistance in the motors changed subtly. This caused a microscopic fluctuation in the torque delivery, which translated into a faint, high-frequency resonance vibrating through the solid steel deck plate of the cab. When a driver felt that specific vibration, they knew they were seconds away from melting the traction motors. They would feather the rheostat throttle, reducing the current draw and sacrificing their speed to save the machine. It was a physical relationship with an invisible force. The operator was literally feeling the electricity. As the M-85 proved beyond a shadow of a doubt that electric drive could conquer the steep ramps and summer heat, it inadvertently triggered its own rapid obsolescence. The Unit Rig Lectra Hall M-85 was a victim of its own flawless proof of concept. Before the 1960s were over, the realization that an electric wheel motor could pull an 85-ton load up an 8% grade without a transmission fundamentally altered mine planning. If the mechanical constraints were gone, the only limit was the size of the electric motor and the rubber on the tires. Almost immediately, the industry demanded more. By 1968, Unit Rig had pushed the design to 100 tons with the M100, and shortly after, to 120 tons with the M120. The M-85, the pioneer that had broken the mechanical barrier, was suddenly undersized. The massive, new 10-cubic-yard electric shovels required larger truck beds to load efficiently without waiting. The M-85 fleets were demoted. They were pulled off the deep primary ore routes and reassigned to upper benches, hauling overburden and waste rock where their smaller capacity would not bottleneck the primary crushers. The trucks that had revolutionized open-pit mining were relegated to the margins of the pit within a single decade. The fleets were largely retired by the late 1970s. The machines that had survived the grueling transition from mechanical to electric drive were eventually stripped for their alternators and grid blowers, and their heavy steel frames were cut down with torches for scrap. But the legacy of the M-85 is absolute. Every 300-ton and 400-ton AC drive haul truck operating in a modern mine today traces its lineage directly back to the moment Unit Rig removed the driveshaft and put an electric motor inside the clowns. Wheel hub. The transition required an entirely new kind of operator, one who drove by the ammeter rather than the tachometer, and who could physically feel the thermal limits of high-voltage electricity through the steel floorboards. The transmission died in the dust of New Mexico. The electric wheel inherited the earth.